What I'm going to show you in this video is a method called substitution, or use substitution, which makes it a little bit easier to figure out antiderivatives or indefinite integrals. You can figure these out by kind of guessing and checking, but what this substitution method does is takes out some of the guessing and gives you kind of a starting point that makes it easier to find the right answer. So this integral right here we know is the result of differentiation. So let's take a look at how substitution would work. I'm going to say that I have a variable u, and I'm going to make that variable equal to an inside function that I observed within this argument of the integral. So I'm going to set u to be x squared plus 1. If I differentiate both sides of that u, I get du dx is equal to 2x. Now, one thing that I can do instead of treating this as a derivative is I can actually use the differential form and actually say that du is equal to 2x dx. And this is where we can start to see the benefit of this substitution method. Because if you notice, here I have 2x dx in my integral argument, and I have 2x dx here as well. So what I can do is write this entire integral as something in terms of u. So instead of 2x dx, I'm going to write that as du. And x squared plus 1, this inside function, instead I'm going to write that as u to the power 50, and I'm just going to leave the integral symbol there. Well, this integral is something that we can just use one of our formulas or some of our intuition about the derivative rules to figure out without trying too hard. This antiderivative is going to be 1 over 51 u to the power 51. And I'm going to add in the plus c now, because we know that whenever we're doing indefinite integrals, we could have a constant there that when differentiated ends up being 0. So it doesn't appear in the argument of the integral. Now that we have this, let's substitute this expression for u back into the integral. Because originally we were given an expression containing x. Let's make the expression we end up with in terms of x. So this becomes 1 over 51 times x squared plus 1 to the power 51 plus c. Let's try another one now. We can see in this function we have a couple different things going on. We have a constant 2 multiplying sine of x plus 9. Now, it's this x plus 9 that I want you to notice is the inside function. And very often, the inside function is what we select for our u. So let's make u equal to, our u equal to x plus 9. We can take the derivative. I'm going to write du here. On the right-hand side, I get 1. And remember, in the last step, this was du dx, but I'm going to write that dx on the opposite side instead. And so now let's substitute these elements into the expression that we're given. So this becomes the integral of 2 times sine of u, and in place of dx, notice that I have 1 times dx, which means that if I simplify this, this is just du is equal to dx, so I can just replace the dx with a du. And now I can use my integral properties to evaluate this. I can pull the 2 out front and just try to find the antiderivative of sine of u du. That becomes 2 times negative cosine of u, which simplifies to negative 2 cosine of u. And just as we did in the last example, let's substitute back in for u to get our actual antiderivative. So u is x plus 9, so this becomes negative 2 cosine of x plus 9. And of course, let's not forget that constant plus c. Let's keep going with our examples. So our inside function on this one we can see is probably 5x, so let's try that out. U is 5x, so du is going to be 5 dx. And so I can again use some algebra, divide both sides by 5 to get that dx then is just going to be equal to 1/5 du. Let's rewrite our integral. This becomes the integral of cosine of u, and dx is now going to be replaced here by 1/5 du. I can factor out this 1/5, so this becomes 1/5 times the integral of cosine of u du. I can find that antiderivative. The antiderivative of cosine of u is going to be sine of u, and simplifying one more step, putting that u back in terms of x, that becomes 1/5 sine of 5x. Now, you might be able to find this without using the substitution method. You might be able to look at cosine of 5x and kind of think backwards to figure out that this needs to be a constant of 1/5, but I think the substitution method does give you a little bit of an option in case you're not able to see that from the beginning. Okay, so another example. This one, again, we're looking for a candidate for an inside function. Let's use u being equal to 1/3 x minus 8, which means du is going to be 1/3 dx. And so spinning that around, that dx is just going to be 3 du. And so let's substitute this back in. So the integral then, dx becomes 3 du over u to the power of 5. And so that 3 we can factor out. 3 times the indefinite integral of u to the -5th du. And now I can just write that thinking about my power rule. That's going to be 3 times -1/4 u to the -4th plus c. Let's put that in at this stage, why not? And so now let's substitute back in this 1/3 x minus 8. So 3 times -1/4 of 1/3 x minus 8 to the -4 plus c. And we'll just clean that up just a little bit to make that -3/4 times the quantity 1/3 x minus 8 to the -4 plus c. And we can differentiate and then use chain rule to show that this is the correct answer. Also know that in case this is something that pops up in a multiple choice question where you have to be able to write it in a couple different ways, since this is a negative exponent now, the other way this might be written is as -3/4 times the quantity 1/3 x minus 8 to the power 4. So in this one, I'm going to purposely make a mistake because I want to show something that will generally happen when you are trying to do the substitution method. You're going to make a mistake. You're going to find that something doesn't necessarily work. So this one is a little bit harder to tell, perhaps, what the inside function is. So I'm going to guess, and I'm going to say that our inside function is cosine of x, which means that our du, taking the derivative here, is going to be negative sine of x dx. And trying to find our same algebraic method, if we solve this for dx, we can get that dx is equal to du over negative sine of x. So that's our du. Let's substitute that in and see what happens. So if I do that, I end up getting sine squared x times cosine of x, which is now u, and dx, oops, made a little mistake there, so this should really be dx here. So I'm going to take this dx expression and substitute it in there. So this is u times du over negative sine of x. And let's now kind of simplify this because we have a sine squared x and negative sine x. We simplify this to become negative sine of x times u du. And I want you to notice that this substitution hasn't gotten rid of our variable x. It's still there. And when you use substitution correctly, when you have found the correct inside function, you should end up with an argument of the integral that has only one variable in it. So we know that this is an incorrect function for u. So let's try another substitution. Let's try the substitution instead. U is equal to sine of x. And if I take the derivative and get the differential, du is equal to cosine of x dx. And notice here in this case, in our original integral, bring that down here, that cosine of x dx is visible right here in our expression for du. Cosine of x dx is equal to du, and sine of x is equal to u. So we can now make our substitution. This becomes the integral of u squared du, and that's a nice clean antiderivative. That becomes 1/3 u cubed plus c. And so now we can substitute back in for u and get that that's the same as 1/3 sine of x quantity cubed plus c. So that's just an example of what might go wrong there. Okay, one last example. As you might suspect, whenever we are doing substitution questions with trigonometric functions, it can be really useful to actually write the functions in terms of sine and cosine. And so this is going to be one such example. I'm going to take this tangent of x dx and rewrite it as sine of x over cosine of x times dx. And I'm going to make a substitution of u being equal to cosine of x, which means that du is going to be equal to negative sine of x dx. Now notice something here. Negative sine of x dx is similar to what we have right here, but I could also say that negative du is equal to positive sine of x dx. And now this expression on the right-hand side is exactly what appears inside the integral right there. So let's make this substitution. So this becomes the integral of 1 over u, because that's 1 over cosine of x, times du. And we've used this integral before. This was a formula that we've discussed previously. This antiderivative we need to write as ln of the absolute value of u. Oh, I'm realizing I forgot one other thing. This was negative du, so this should be negative du right here. This is negative ln of u, and now I can add in my constant, and then I can do the substitution of my expression for u. So this becomes ln of cosine of x plus c, and of course that's going to be the absolute value. So that's a few examples of how to use substitution to evaluate indefinite integrals.